Hello everyone. So, in last module we discussed about the finite volume discretization of diffusion equation. So, now we will add the convection term and we will discretize the steady convection diffusion equation using finite volume method in this module. In this lecture, so first let us write the governing equation. So, we are considering 2D steady. So, we have convection term as well as diffusion term. So, convection diffusion equation. So, the governing equation is rho u phi by del x, where rho is the fluid density and u is the velocity in x direction. Then rho v phi by del y, v is the velocity in y direction, is equal to del of del x gamma del phi by del x, gamma is the diffusion coefficient, plus del of del y gamma del phi by del y plus s. So, we have written this governing equation for general variable phi and u v are the velocities in x and y direction. So, if velocities are known, obviously this equation is linear. So, for known velocity, okay, the above equation is linear. So, we discussed that if this is your x direction, this is your y direction, then u is the velocity in x direction, v is the velocity in y direction, and I is the unit vector in x direction and j is the unit vector in y direction. Now, let us consider this finite volume, okay, of cell P. So, you can see this is the main control volume, this P, and the phase centers are small e, small n, small w and small a. So, we will integrate this governing equation over this control volume, okay, main cell P. So, let us write this governing equation in vector form first and write in terms of the flux vector. So, the governing equation you can write in vector form as divergence of rho u phi is equal to divergence of gamma grad phi, okay, plus the source term. So, you can see that u is obviously your velocity vector and now we can write as divergence of rho u phi and this diffusion term you bring in left hand side. So, what you will get? Divergence of minus gamma grad phi is equal to s. So, now we will introduce the flux vector j is equal to s, where j is the flux vector rho u phi minus gamma grad phi. So, j is the flux vector. So, in last module you have seen this flux vector contain only the diffusion term, but in this lecture you can see this flux vector contains convection term as well as the diffusion term. So, the first term is the convection term and second term is the diffusion term, and this equation divergence of j is equal to s you have already discretized in last class and you know all the assumptions involved while integrating this equation in the main cell P. So, we will follow the same procedure, we will have the same assumptions valid here and we will write the discretized equation for this divergence of j is equal to s. So, first integrate over this control volume. So, divergence of j is equal to s, we are integrating over the main cell P, divergence of j dv plus equal to volume integral s dv. Okay. Now, use Gauss divergence theorem. So, you can write integral. So, now we are converting the volume integral to surface integral. So, J dot ds is equal to volume integral S dV. We followed the same procedure. Till now we have not assumed anything. Okay. Now, we will assume that J varies linearly along the faces and the average value lies at the face center. So, face center small e, small n, small w and small s, and for the volume integral of the source term also we will have the average value lies at the cell center P. So, with that now we can write this integral over the faces, that we can write summation of J f dot S f. So, S f is the surface vector at the faces equal to S bar is the average value lies at the cell center P and delta V. So, this now we can write J E. So, we have 4 faces for these 2 dimensional cases. So, east, west, north and south. So, we will write J E dot A C plus J W dot S W plus J N dot S N plus J S dot S S is equal to S bar delta V. So, now each flux vector at the faces we have 2 terms, one is convection term and diffusion term. The diffusion term already you know how to discretize. So, we will have the assumption that the flux while calculating the flux vector we will assume that the value of phi varies linearly between the cell centroids. So, obviously, the gradient of phi at the face center we will calculate using the neighbor cell centroid value and the its main control volume cell center value. So, first let us see that how we will calculate the J E dot A C, then similarly we can write for other terms. Okay. So, J E dot A C, what is J? So, J is rho u phi minus gamma grad phi. Okay. So, now J E will be rho u phi at face E minus gamma grad phi at face E. Okay. What is the surface vector AC? AC is AEI. Okay. So, now you can see this is your JE, this is your AC. So, now if you make the dot product, and what is grad phi? Grad phi is del phi by del x I plus del phi by del y j. Okay. So, now you make the dot product and write the term. So, convection term, if you see, this is the convection term rho u phi E. So, u is again u I plus V j. So, if you make the dot product with u and A C, then you will get only u e a e. Okay, u e a e, because I dot I will be 1 and I dot j will be 0. So, only this term will remain u e a e. So, it will be rho u phi at east face into A E minus gamma del phi by del x, because it is grad phi del phi by del x I and you are making the dot product with A C. So, del phi by del x into A E. So, del phi by del x at east face A E. Okay. So, now we can rearrange it. So, we can write as rho u a at east face and phi you are taking outside of this and minus, now you can see gamma e a e and del phi by del x at face center E. Okay. So, that we will use phi e minus phi p divided by the distance between these 2 cell centers. Okay. So, now this will represent as mass flow rate Fe, okay, into phi e, and gamma e a e by del x e will represent with d e into phi e minus phi p. Okay. The last term already you have discretized, okay, in earlier lectures, but the first term now we are introducing with the mass flow rate F e. So, we are introducing mass flow rate, okay, F e is equal to rho u e a e. Okay. So, now you can see that u e, the velocity at the phase center E, this is not known, because you might have the values available at the cell centers P. So, you can use a linear average. Okay. So, you can use as rho, if you have a uniform grid, then you can write u e plus u p divided by 2 into a e, okay, where we are assuming uniform grid. Okay. So, now F is the mass flow rate and phi e is the value of phi at the phase center. So, this is also unknown, right. Phi is also unknown, because phi you are solving only at the cell centroids, but you need to find the value of phi at the phase center small e. So, for simplicity let us use the central difference, and phi e, okay, we can use the value of phi e plus phi p divided by 2. So, this is known as central difference convection scheme. Okay. So, if you see F e phi e, okay, the value of phi e sometime will determine depending on the value of F e, okay, whether it is positive or negative. So, phi e is known as convective coefficient and phi e is known as convected variable. So, you can see phi is the convected variable. So, this mass flow rate, whatever F is there, it is known as convective coefficient, and due to the mass flow rate this phi is transported. Okay. So, that is why it is convected variable, and to determine the value of phi e from the sign of F e, we will use some convection schemes and we will discuss in later classes. So, now for this, if you use that central difference convection scheme, phi is equal to phi e plus phi p divided by 2 for uniform grid. Okay. For uniform grid, then what you can write now, J e dot A C. So, let us write down. So, J e dot A C, now we can write F e by 2. Okay. Then we have a average value phi e plus phi p minus d e convection term and phi e minus phi p. Okay. So, we have written this flux vector dot product with the surface vector at the east face. Now, let us write for west face. So, J w dot S w, similarly now you can see it will be rho u phi at west face. Okay. Now, if you make the dot product with J w with the S w. So, J w is rho u phi w minus gamma grad phi at w, okay, and S w is minus a w I. Okay. So, this you have to remember, because this is minus, because at this phase your phase normal in negative x direction. Okay. So, that is why it is minus AWI. So, now if you make a dot product, obviously it will become minus AW. Okay. Similarly, here also you will get minus 1 convection term is there and another minus will come, it will be a dot product and you will get plus and you will write gamma W, okay, AW and del phi by del x at W. Okay. So, now you can write it. So, now you use the convection minus FW phi W, okay, and plus gamma W AW. Now, del phi by del x at W. So, it will be phi p minus phi W divided by delta x W. Okay. So, now we rearrange it. So, you will get FW will take the convection scheme, okay, central difference convection scheme. So, minus FW by 2. So, it will be average of phi p plus phi W by 2. So, it is phi p plus phi W and this is your plus dE and phi p minus phi W. Okay. Now, similarly, if you do Jn dot Sn, so you can write as Fn by 2 phi n plus phi p minus dn phi n minus phi p. Okay. So, this is your convection term, diffusion term, where Fn is, now you have rho Vn into An, okay, because now you have the u velocity and Jsn is your Anj. So, now if you make a dot product, so it will be Vj dot An j. So, it will be Vn and that rho Vn An we are writing as the mass flow rate at north phase Fn. Okay. So, similarly, you can write Js dot Ss. So, it will be Fs by 2. So, you remember we are using central difference convection scheme. It will be phi p plus phi s and here minus sign will be there because Ss will be minus Asj. Okay. So, due to that minus sign will come and you have plus ds phi p minus phi s. So, we have written all the terms. Now, let us put in the summation of Jf dot Sf is equal to S equation. So, we have Je dot Ac. So, here Fs will be rho Vs As. Okay. So, Ac plus Jw dot Sw plus Jn dot Sn plus Js dot Ss equal to S bar delta V. Okay. So, now let us put all these values. So, you can see here it will be Fe by 2 phi E plus phi P minus dE phi E minus phi P. So, this is your Je dot Ac plus Jw dot Sw, this one you write. So, you can write minus Fw by 2 phi P plus phi W plus, sorry, here it will be dW. Okay. So, it will be dW phi P minus phi W. So, this is for the west phase. Now, for the north phase, the fluxes plus Fn by 2 phi n plus phi P minus dN phi n minus phi P minus Fs by 2 phi p plus phi s, and you have plus ds phi p minus phi s equal to s bar delta b. Okay. So, now we will write this equation in the form of A p phi p. So, you collect all the terms of phi p in the left hand side and rest all other terms you take in the right hand side. So, which are the p terms? So, this is, so these are the phi p terms. Okay. So, all these coefficients we will write in the left hand side. So, if you write that, so you see it will be f e by 2 and minus minus plus. Okay. So, this will be plus d. So, we will write d e plus f e by 2. Okay. Similarly, here you see this is your d w plus d w. So, plus d w, and here phi p coefficient is minus f w 2. So, minus f w by 2. For north face you can see this is your minus minus plus. So, it will be d n plus f n by 2 plus for south. So, it will be phi p. So, it will be d s and it will be minus f s by 2. Okay. So, these are the coefficient of phi p. So, this is your diagonal coefficient. Okay. Equal to, now other terms you take in the right hand side. So, if you take phi e term, okay, then you take phi w, okay, then you take phi n and you take phi s, okay, in the right hand side. So, you can see, so if you write the coefficient of phi e, then you can see phi is here minus d e phi e. So, right hand side if you take, it will be positive d e, and here you see f e by 2 phi e. So, it will be minus f e by 2 here. So, it is coefficient of phi e. Similarly, now you see phi w. So, here minus d w phi w. So, it will be right hand side if you bring it, it will be d w, and here you have minus f w by 2. So, it will become plus f w by 2. Okay. Similarly, for north it is d n, it will be minus, because left hand side you are bringing to right hand side. So, it will be minus f n by 2 phi n and phi s. So, it will be plus d s plus f s by 2 phi s is equal to s bar delta b. Okay. So, now these coefficients you just write it as coefficient a e, this is as a w, this is as a n, and this coefficient as a s. Okay. So, if you write that, then what you can write the left hand side term, this first coefficient you can see. So, we will denote it as a p. Okay. So, this will denote as a p. So, a p you can write as d e plus f e by 2 plus d w minus f w by 2 plus d n plus f n by 2 plus d s minus f s by 2. Okay. So, we will rearrange it. Now, you can see a e is d e minus f e by 2. So, we will write first this term as d e minus f e by 2. Okay. So, if you write d minus f e by 2, then another f e by 2 we have to add. So, f e by 2 plus f e by 2. Okay. So, this is your will get cancelled. So, f e by 2 will remain. Now, this together you can see it is f e. Okay. This together this is f e. So, similarly, you can write d w. So, now we have in AW coefficient DW plus FW by 2. So, we will write FW by 2, okay, and we will subtract FW by 2, and another minus FW by 2 is there. Okay. So, now these together will give minus FW. Similarly, dn, so n contains minus Fn by 2. So, we will write minus Fn by 2 plus Fn by 2 and another Fn by 2 is there. So, these together will give Fn and plus ds plus Fs by 2, okay, and we have now subtract minus Fs by 2 and another Fs by 2 is there. Okay, so, these together will give Fs. So, now this Ap we can write as, you see, this term, okay, this is n, okay, this term, this is your AW, this is your AN and this is your AS. So, we can write as A east plus this is your A west plus AN plus AS. So, these are the coefficients, and we have now these together, okay, will give you plus Fe minus Fw plus Fn minus Fs. So, now you can write Ap as AE plus AW plus AN plus AS plus Fe minus Fw plus Fn minus Fs, and this you can write as summation of A and B, because all the neighbor coefficient summation, plus summation of Ff. Okay. What is Ff? So, what does it signifies? Fe minus Fw minus Fn minus Fs. Okay. So, this is the net outflow from the control volume P. Okay. So, that means it is the continuity equation. So, if you integrate the continuity equation over this volume, then you will get this. So, that means summation of Ff is Fe minus Fw plus Fn minus Fs, and you know what is Fe? Fe is rho Ue Ae. Okay. Ae is your delta y minus Fw is rho Uw delta y plus Fn rho Vn, okay, Vn, and the area is delta x and minus rho Vs into delta x, and this is the net mass outflow from the cell P. Okay, net mass outflow from the cell P. So, you can see that if your flow field satisfies the continuity equation, then summation of Ff will become 0. Okay. So, generally at convergence summation of Ff will be tending to 0. So, now you can write now the final form of the discretized equation. So, you can write Ap phi p is equal to Ae. So, you look this one. So, this is your discretized equation. So, you can write Ae phi e plus Aw phi w plus An phi n plus As phi s. Okay. Sorry, this is will be plus. So, plus S bar delta V. So, we can write Ae phi e plus Aw phi w plus An phi n plus As phi s plus S bar delta V. Okay. So, this now we can write as Ap phi p is equal to summation of An b phi n b, okay, all the neighbor An b phi n b plus, so S bar delta B will denote as B. Okay. So, you have B is equal to S bar delta V, Ae is your dE minus Fe by 2, Aw is dW plus Fw by 2, An is dn minus fn by 2 and as is ds plus fs by 2, and the diagonal coefficient ap will be just ae plus aw plus an plus as minus summation or plus fe minus fw plus fn minus fs. So, you can write APS summation of all the neighbor coefficient plus summation of FF. Okay. And what about your FEFW? So, FE is rho UE AE. Okay. A is nothing but your delta y. FW is rho UW AW. Fn is rho Vn An and Fs is rho Vs As. Okay. And you have dE. So, dE will be gamma E AE divided by delta XE. dW is gamma W AW delta XW, and dN is gamma N AN by delta XN, and ds is gamma S A, sorry, here delta Y. So, this is your delta Y and gamma is S by delta Y S, where AE is equal to AW is equal to, this is the surface area. So, that is your delta Y, and A north is equal to A south is this distance. So, it will be delta x. So, it will be delta x. So, you can see. So, this is the final algebraic equation for this steady convection diffusion equation, and this you need to solve using some linear solver, and where phi p denotes phi ij, phi e denotes phi I plus 1 j, phi west denotes phi I minus 1 j, and phi north denotes phi I j plus 1, and phi south denotes phi I j minus 1. So, in today's class we discretize steady convection diffusion equation. So, we considered 2-dimensional case, and we introduced the flux vector which contains diffusion term as well as the convection term. Then we integrated this over this control volume P, and we have converted the volume integral to surface integral using Gauss divergence theorem. Then each flux vector at each faces, okay, the flux vector dot product with the surface vector we have calculated at each faces east, west, north and south, and we defined the mass flow rate Fe as rho UE AE, and similarly for the north face Fn is equal to rho Vn An, and finally after rearranging we have written the discretized form in the form of AP phi p. So, we have written AP phi p is equal to summation of A n b phi n b plus b, where AP is the diagonal coefficient, and this diagonal coefficient AP is equal to summation of all the neighbor coefficient. AP is equal to AE plus AW plus A north plus A south plus the summation of FF, where summation of FF denotes the net mass flow outlet from the cell P, and it actually is the discretized form of the continuity equation. So, if your flow field satisfies the continuity, then this summation of FF will become 0. Thank you.